two equivalent pictures that we've talked about in quantum mechanics a little bit, Schrödinger picture and the Heisenberg picture, can be described in the following way. In the Heisenberg picture, the operators are time dependent, but the wave functions themselves are not. In the Schrödinger picture, which we've used quite a bit more, it is the operators that are do not depend on time, but the wave functions are the ones that have the time dependence in them. So I want to look at, one of the things that we can do today is look at the equivalence of the two approaches and show why that happens. So suppose we apply a time translation operator to wave functions and operators themselves. So I'm writing this again in the Heisenberg picture. Suppose I have a particle of mass m, it's at rest, or I should just say it's particle of mass m, and in one dimension, I'll write the Hamiltonian the following way. P squared over 2m plus v of x. Let's find the position operator for this Hamiltonian in the Heisenberg picture for an infinitesimal time translation. We'll call that delta. So in that case, u of delta is approximately, because delta is small, I delta h bar, I delta h over h bar. Therefore, I can write my position in the Heisenberg picture as a function of delta as approximately 1 plus I delta h over h bar, x operator 1 minus I delta h over h bar. And I can approximate this as x minus I delta over h bar, commutator x h, which works out to x operator minus I delta over h bar I h p divided by n. So x, then in the Heisenberg picture, my x operator can be written as a function of delta as, we'll write it as x h of 0 plus 1 over m p sub h of 0 times delta. Example of this, let's apply it to the one-dimensional harmonic oscillator. So in that case, h is equal to p squared over 2m plus m omega squared over 2 times x squared. Let's find the position operator in the Heisenberg picture. So we want x sub h at time t. So first thing we do, let's consider the action of x sub h on a stationary state psi sub n. So this will allow us to replace my Hamiltonian operator with just an energy. So I can write e to the minus I h t over h bar. I'm going to write that as e to the minus I dt over h bar. That simplifies things a little bit. So x of t operating on psi of t is u dagger x operator u psi sub n of x, which I can write as e to the I ht over h bar times h bar over 2m omega, a plus dagger minus, I'm sorry, plus a minus dagger, my raising and lowering operators, e to the minus I h t over h bar times psi sub n of x. This can be written as we said before, e to the I e t over h bar. And so I can put this together and write it as square root h bar over 2m omega e to the minus I e over h bar times n plus 1 psi sub n of x plus square root n psi sub n minus 1 of x. Okay, it's h bar over 2m omega square root e to the minus I e sub n t over h bar square root n plus 1 e to the I e sub n t over h bar times psi sub n plus 1 of x plus square root of n e to the I e n minus 1 times t over h bar psi n minus 1 of x. Altogether, that just means x in the Heisenberg picture looks like square root h bar over 2m omega e to the I omega t, a plus e to the minus I omega t, a minus, which I can write then as x sub h of t is x sub h of 0 cosine omega t plus p sub h of 0 over m omega times the sine of omega t, where omega is just e over h bar. Notice, this expression would satisfy the classical motion for a spring. Now in the Schrodinger picture, the wave function is what evolves in time in the following way. And in this case, we're writing x, operator is just x, and the p operator as minus I h bar d dx. And they, of course, have no time dependence because they're in the Schrodinger picture. Only the wave functions have time dependence. So in that case, the time dependence of the expectation values just come from the wave functions themselves. In the Heisenberg picture, the wave function is constant in time, but the operators evolve in time, as we said. So something in the Heisenberg picture, we might have something like this QH of t. I can write as U dagger of t operating on Q times U of t. And therefore, my expectation value for Q would be psi h Q psi h. So the two pictures are essentially the same. It's the equivalent picture. An analogy you might use is, on an ordinary clock, the hands move, but the numbers remain fixed. On the other hand, you can also look at it as the numbers moving counterclockwise and the hands remaining fixed. So when we talk about time translation invariance, if the Hamiltonian's time dependent, we can write the formal solution to the Schrodinger equation in terms of u. So I can write psi of x and t is u for t and t naught applied to psi of x and t naught. Where in this case, u I can write as t naught plus delta t naught, or approximately 1 minus I h of t naught times delta over h bar. So kind of similar to what we did with rotations and translations in space. Time translation invariance tells us that the time evolution is independent of which time interval we consider. So if a system starts, let's say in state alpha at t1, and it evolves for some time delta 1, it'll end up in some state beta, as if the system started in the same state alpha at time t2 and evolved into the same time, at the same time. So another way of saying this is h of t1 is equal to h of t2, which tells me dh dt is 0. By the Ehrenfest theorem then, I over h bar, h commutated with itself is of course going to be equal to 0. What that implies is that energy conservation, energy being indicated by the Hamiltonian operator, energy conservation is a consequence of time translation invariance. So in this example, we're saying h of t1 is equal to h of t2, which tells me dh dt is 0, and therefore, by Ehrenfest theorem, it must be that h commutes with itself, and therefore, this time translation invariance is indicative of a conservation of energy. So to sum up, when we talk about the examples of Noether's theorem, time translation invariance implies a conservation of energy. Space translation invariance implies a conservation of linear momentum. And rotational symmetry, rotational invariance, implies a conservation of angular momentum. As I said, these are just 3 examples of how Noether's theorem works, and you'll study others in your future physics courses. Well, next time, as we promised before, we will start perturbation theory.